All right, so in 14.4, we're going to talk about trees. And what we're doing in this section is we are going to find an efficient network for linking a set of vertices in a graph. So before I get to the definition, I want to just think about what we might typically think about when we hear the word tree. So this is what I'm going to do. I'm going to draw something that kind of resembles a tree that you think about, like a traditional tree or a tree in the traditional sense. But I'm going to add these vertices. So you might have a branch this way. Let's see, A, B, C, D, E, F, G, H. All right, so this is a decent looking tree, I suppose. But I use this as an example to kind of give you an idea of what the definition of a tree is for this section. And so this is an example of what our definition is going to tell us about a tree. Basically doesn't have to look like this. It doesn't have to have kind of an origin point, if you think about it that way. But what has to happen is every connection, every vertices can only be connected by one edge. You can think that every edge is a bridge. So if I were to remove this edge, then B and A are no longer connected. If I were to remove this edge, E and C are no longer connected. So that's essentially it. So a tree is a graph that is connected, but no circuits. So if, for instance, F and E were to connect, it would no longer be a tree because then we would have a circuit. This would be all connected. All right, so all trees have the following properties. There is only one path joining any two vertices. Every edge is a bridge. And then finally, I didn't mention this, but a tree with n vertices has n-1 edges. So in this example, 1, 2, 3, 4, 5, 6, 7. Oh, I didn't label this one. Let's do that. F, G, H, I, J. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so this guy has 10 vertices. And by the definition, it should have 9 edges. So 1, 2, 3, 4, 5, 6, 7, 8, 9. It does. Okay. All right, so I want to give you some examples first of what some trees might look like. I mean, this is a good example, I think, but if you see them in the homework, you might see them a different way. So let's look at this one. This one reminds me of a snowflake in its shape. So we'll call this part A, B, C, D, E, F. So that's one. And then you also could have something that looks like this. I'm going to just draw my vertices. A, B, C, D. And so it could almost look like a straight line or a zigzag line or something like that. Okay, so if those are examples of trees, then let me show you some examples of things that are not trees. So let me take something that looks like this. First, I'm going to draw this exactly. And then by doing this exercise, I'm showing you, in case they ask you in the homework, to take this tree and connect some edges so that it's no longer a tree. So could you connect any of these edges so that it no longer makes a tree? And in fact, if I connect any of these other two edges together, we no longer have a tree. So here's an example where it's no longer a tree because that is now a circuit. Okay. This is now a circuit. And then I'm going to take this guy. I'm going to draw my 4 vertices out. And then just to show you the difference here, I want to not connect. Okay, so this is all one graph. Since this is not connected here, this is not a graph. These are not trees. Since it's right here, I'm going to do it. Let's see how many vertices this has. Going back to the example of a tree, 1, 2, 3, 4, 5, 6. So this has 6 vertices. So it should have 5 edges. 1, 2, 3, 4, 5. And then this one, even though it looks like a straight line, it has 4 vertices and 3 edges. Okay, so let's move on. So now we come to a new definition. By the way, we're probably just going to have one video for 14.4. It's a pretty brief section. We'll have one note video and probably one homework video. All right. So a spanning tree is a subgraph, meaning it's essentially going to look like the parent graph that contains all the connected graph's vertices. Okay. So we're going to take the same graph and all the vertices, and we're actually going to connect them the same way, and that's what I say down here, just to emphasize it. The graph also has to be connected and contain no circuits. So let's take an example. Okay, that might be a little weird, so let's just take this example. All right, so given the following graph to the right, notice this is not a spanning graph. This is not a spanning tree. Or this is not a tree. This is just a graph. But I'm going to take this and I want to make some examples of possible spanning trees. Now, there are multiple solutions. So, solutions. So here's the thing. I have to have all of my vertices. I'm going to go ahead and label, or I'm going to just draw out in space all my vertices. I don't have to have each of these lines. In fact, we're trying to kind of make the most minimal network so I can get from A to F through all of these the shortest way, or A to E the shortest way or something. Okay. So I want to connect these, but I don't want any circuits. Notice ABC is a circuit. Okay. So if I go from A to B, all right, I can't go from B to F because BF is not in the original graph. All right, I can either go from A to C or B to C. I'll go to B to C. Okay. At this point, I could go C to F or C to D. I'm going to go C to F because that was in the original. And then I could still go from C to D or E to F, but not both. So I'll go E to F and D to E. So this is a spanning tree of the graph. That's one example. So that's one solution. Here's another. This is also a solution. I'm just going to do a different one. And then I'm going to give you an example. I'll do this one smaller. I'm going to give you an example that is not going to work. But this one is going to be a solution. So let's do that. I'm going to kind of make it smaller because I want to put another answer that's actually going to be wrong on here. So let's see. All right, so this one is also going to be correct. So I could go from A to C, and then A to B. I could have gone A to C and C to B. I could go, let's see, C to D was in there. D to D. Okay, that's another one. You'll see some homework problems that kind of look like that. So in this little space I have left, I'm going to say the following is an incorrect solution to this problem. Okay. And I wanted to mark it off. These two guys are good. They get check marks. Okay, they're fine. But this one I'm about to do is going to be wrong. So let me draw my vertices again. I just want to show you the difference between a correct answer and a wrong answer. Okay, here's all my vertices. So I said earlier I could do this, okay, but let me see. I'm going to go ahead and finish this out, and then you can pause the video and see where you found the mistake. All right, so I'm assuming you've looked, maybe paused it, but the problem here is BF was never in the original graph, okay? BF was not part of original graph. Okay, so this is, you're gonna get this one marked off. Okay, but that's all there is to it. It's pretty straightforward. You just have to know the rules going in. All right, and then we got one more definition and one theorem, and that's it for this section. So the next definition is a minimum spanning tree. In order to do this, we need a weighted graph. We talked about weighted graphs in the last section. That just means I put some numbers next to my edges. All right. So a minimum spanning tree for a weighted graph is a spanning tree with the smallest possible weight sum. Okay. Kind of reminded me of the nearest neighbor. It's not quite the same, but we're still trying to minimize things. And we can do that. We can answer that question by using Kruskal's algorithm to find that minimum spanning tree. So Kruskal was a recent mathematician. I think he passed away in 2010. So any type of math that's done in the 20th century is a new development. Theorems that come out that late are pretty new. All right, so let's look at Kruskal's algorithm. So let's fix this. All right, Kruskal's algorithm. What we mean by an algorithm is the process. How do we do it? So this is how we can do it. We first find the edge with the smallest weight in the graph. So we'll have this weighted graph. We find the smallest edge or edges. There might be two. I'm going to say that. might be 2 with same value. So if the smallest number in my graph was 10, but there happened to be 2 of those 10s, then I would choose both of them. If there were 3 10s, well, I'd have to be careful because 3 edges can make a circle. Okay, so if I have 2 edges, A and B, I'm taking a slight detour, but if I have 2 edges, A and B, that can't make a circuit. Okay, so 2 vertices alone can't make a circuit, but 3 can. Okay, A, B, C, 3 edges can make, or maybe I should say, no. 2 vertices alone can't make a circuit, but 3 can. That's why we have to be careful. Once we get the first 2 smallest numbers, so either we did that in step 1, or if the smallest number was an 8 and the next smallest is a 9, then we use the second one. Okay, so we're looking for the first 2 smallest numbers. Okay. The problem is when we get to step 3 is it cannot make a circuit. So when we're looking for the third smallest, that cannot make a circuit. Okay, that might be a little confusing, so let's just look at it in practice. Oh, and then step 4, we keep doing step 3 until we basically finished. All right, so let's look at an example. This is a weighted graph because there are numbers. Let's see if we get that fixed. Okay, I was trying to get it in focus. All right. So the way I'm going to do this is I'm first going to list all of the edges, all of the weighted edges. List all of the weighted edges in order from smallest to largest. Okay. And as I do it, I kind of want to make sure I got everything. So I'm going to circle these as I go along. And circle them as we list. I do that so I'm not doubling up and then I'm not forgetting. Okay. So the first one I see is 1. That's the smallest. Circle that. It's probably hard to tell in the video, but I'm using a purple pen. The next one, I look around. This next smallest is a 2. Now, I will start worrying about circuits in a little bit. The first thing I want to do is just list everything I've got. Okay, keep looking, getting bigger. 3, 3, there's 2 of those, so I'm going to list both 3 and 3. You could write the edges out, doesn't matter, because you got the picture right here. Then we got a 4, 2 5s. Don't want to see. The next ones I got is 8 and a 9. So let me write those out. 8, 9. I'm going to circle them because I've taken care of them. Okay. All right. Now, I am going to start with my smallest 2 edges because I cannot make a circuit with only 2 edges. So I am going to highlight those edges If they were the same number, if I had two edges that were both 1, I would highlight both of those. But my two smallest are 1 and 2. So let's highlight those. Okay, now we get to the third largest, which is 3. All right, it doesn't matter which 3, honestly, but let's say I choose this 3 since it's top left. Okay, it does not make a circuit, so I'm going to highlight it. In fact, as I highlight each of my edges, I'm going to highlight those numbers because these are the numbers I'm going to end up adding up. All right. I could choose the other 3 because he does not make a circuit. So got that one. Now let's go to 4. Does the 4 create a circuit? It does not. So 4 is good. So it looks like we're just going to highlight everything. All right. Now I get to the 5. Here's where our issue lies. I can highlight either of these 5s, but I cannot highlight both of the 5s because if I highlight both, I will create a circuit. Okay, can't do that. So choose a 5. It does not matter which. I'll just choose this one, and I'm going to highlight the second one just to change it up. Now, I move to my next number, which is 8. Okay, so I'll go to 8. Now, does that 8 create a circuit? It does. If I highlight the 8, then I've created the circuit. So I'm going to X out what I'm not using. Okay, so skip that and move on to 9. If I highlight the 9, that will also create a circle. So I can't use the 9. And so my resulting minimal spanning tree is going to be all of these numbers that I've added up. Minimum spanning tree will be all of these numbers. 1 plus 2 plus 3 and 3 plus 4 and one of those 5s. 1, 2, 3, 3, 4, 5. Let's see, that's 9 plus 1 is 10. 10 plus 8 is 18. Unless I missed something. Oh yeah, because in my example I worked out, I actually had both of the small numbers as 2, but I wanted them to be different, so I changed that. All right, so that will do it for 14.4. The next video I'll do will be some homework, probably just a handful of problems.